Okay, so I'm going to switch around my slides a little bit after seeing Peter Orban's talk on the first day to give you a little more overview of what it means to do relational learning, so you can understand better the sort of key message that I want to convey about a series of work that I'll show you. So I have three pieces of work from two of my PhD students who've now graduated, Rongjing Zhang and Hoda Eldardiri. And so I won't go over the technical details of that work, but I just want to highlight a couple findings that we have been thinking about in relation to the effect of the graph structure on these networks that we're modeling and the performance of machine learning methods that we need to do estimation and prediction in these networks. And so I guess first I should clarify the difference. Let me go to this slide. Clarify the difference between what I'll talk about and what Art talked about at the beginning. So really what we focus on is learning predictive models of attributes in attributed networks where we have the nodes or people or computer hosts or events. The edges in the graph are relationships between those users. And then we have some set of attributes, covariates, on the nodes. So we might have some class label here that I'm coloring as red and green, which is our y's that we're trying to predict. And we have a bunch of other observed attributes x that we'll use to improve that prediction, but we're also exploiting the graph structure. So a big difference between what Art talked about and what we work on is generally we focus on discrete data rather than continuous data and the Kriging models that he was talking about. And also, I think in the set of work that I'll talk about here, we want to learn the models of the relationships in the graph from one part of the graph and then generalize to other parts of the graph instead of the semi-supervised kind of framework Art was talking about. However, there are other similarities that I'll try to point out as I go through the talk. So there's been a lot of work over the last 10 or 15 years on developing methods that can do prediction in this kind of domain. And basically, a number of them can be characterized as modeling the full joint distribution over the y values, which are the class labels on the nodes, conditioned on the observed x attributes that we have and the graph structure. Okay, and so we have a lot of empirical success on learning these kind of models and using them to improve predictions in the networks, and I'll show you that examples in a second. But the key message that I want to give today is that in the machine learning community, in the statistical relational learning community, we've focused on doing this kind of modeling, and what we haven't really thought much about is this graph structure over here that we're conditioning on. And it turns out that the structure of these graphs actually affect how our models work, and both in terms of how the estimation methods work, but also in terms of how the prediction methods work. And so I'll try to elaborate that on that a little bit in this talk. I guess I should explain this conditional distribution. So we also instead of modeling the full joint distribution, some methods model the conditional distribution of predicting a particular label yi, conditioned on the attributes of both that node and its neighboring nodes and the class labels of those neighbors as well. And so basically the graph structure gives us the mechanism by which we identify other related nodes in the graph that then we can use their labels to improve prediction. So that's what we're trying to exploit. And here are some examples of networks where we apply these kind of models. So it ranges from looking at social networks, like what L.I.D talked about before the break, of trying to predict properties of people, let's say in Facebook, predicting their political views or their religious views based on their relationship to their friends in the network, to also gene and protein networks like Bin talked about earlier, where maybe we want to predict the protein function based on its interactions with other proteins in the cell. Okay? And so the key sort of challenges in this area of relational learning are what we focused on for the last 10 or 15 years is that all of the methods that were developed in traditional or conventional machine learning, where we assumed that the data were independent and identically distributed instances, that no longer holds in these network domains. And so we have heterogeneous interdependent instances. We might have partially observed networks with partially observed labels, which is the kind of thing that Art was talking about. The networks themselves might be dynamic or non-stationary. And a sort of key difference with anybody who's from the structured machine learning community here is that we often focus on data from a single network or a small number of networks. So we don't have many, many replicates of these networks where we can talk about asymptotics as we observe an infinite number of networks over time. Okay, so the general form of the models that I'll talk about today can be characterized as Markovian relational models, where this applies to both relational Markov networks, Markov logic networks, and relational dependency networks. There's probably others that fall in this same general category that I'm not aware of at this point. But the form of these models are that we take a model template, which we're calling, which we can talk about as clique templates, and we have these little model templates that the way that we deal with heterogeneity in this graph is we take these little templates and we roll them out over the graph to construct this likelihood like we have here. So we have, I'm pulling the graph structure out here, but we're trying to model the joint labels over all of the examples. And here we have a product over all possible templates, clique templates, then we have instantiations of those templates, and then we have the features of those templates in the model. And so that might look like, a template might look like in this graph right here, where you have the green nodes and all of the brown nodes that they're connected to. You might have a template that applies in that case and looks at the features of those kind of nodes, and then you would roll that out in all of the places that it applies in this particular form of the network. And so what you can notice here is that if you had a template like this, you would have to deal with the fact that this green node right here has 8 neighbors, but this green node down here only has 7 neighbors, right? So there has to be some kind of aggregation or something that deals with the heterogeneity that way, okay? And so here's the part of the slides that I've added in since this workshop has started. I think what gets lost a lot when we just look at math, like I just showed you, is actually how that's operationalized, in these networks and what kind of models we're actually talking about. And so there's a big difference between, well, not a big difference, but an important difference between what I would call the data network and the model network that we end up using for modeling. And so, as Michael alluded to at the beginning, this really comes into play because what we do is essentially roll out a graphical model over the network that we observe. And so the way that looks like is that we might have a data network right here where these would be people and their friendship relationships in Facebook or something like that. And in contrast to people that are just modeling the graph structure, what we now think about is that we have a number of attributes on each of those nodes. And so then the data network really looks like this to us, where we now have these nodes that have a number of attribute values in them. And now I've colored them again according to their class label. If, for example, if we're trying to predict, let's see, which one did I do? Political views, we have the Democrats colored as green and the Republicans or conservatives colored as red. All right, so this is still our view of the data network. And now when we're going to learn a model of this in this general graphical model framework that I talked about, we're going to take our little model template, where here I've used relatively simple cliques, where these are the kind of cliques you might use in an I.D. scenario, where you're talking about the relationship between our 3 different covariates here and their relationship with the class label that we're trying to predict. But then also we have this additional, I think I animated that. This is the sort of key relational part of the model, where we have a template that looks at the relationship between the y values on neighboring nodes in the graph. And so now, once we've defined this model template, what we do is put that together with the data network, and then that will roll out over the entire data network to create this complex graphical model that we'll use for learning and inference. right? And I should point out that this graphical model will look different on the network that we use for estimation and compared to the network that we will use for prediction, because the structure of that network might differ a little bit, right? So what you can see here is we have these little templates that are rolled out over each of the nodes in the graph, and then we have the connections between the y values, okay? Oh, and I had that animated to just show you here. This was the underlying data network that a lot of networks people would present to you and talk about modeling, right? So the key point that I want to make here is that the structure of this rolled out graphical model that we're going to use for learning and inference depends on the structure of the data network that we're using for analysis. And this particular kind of structure can impact the performance of our models. And so in contrast with graphical model people who try to reason about the performance of arbitrary graphical models that maybe have nice structures like trees, or maybe talk about cases where the cycles cause problems in the inference, now we're doing the kinds of graphical models we deal with have very specific kinds of structure because they have the properties that have been talked about, all through this workshop, that we have these very specific kinds of social network properties, right? And so in particular, they're sparse and likely to be clustered, okay? And I should note also at this point that I showed you a relatively simple example where I could lay the original data network over top of exactly the graphical model that I constructed. But if you had more complex clique templates that considered more than just binary pairwise cliques between the users, this graphical model structure would get much harder to draw, right? And so that's why many of us that gives talks on these kind of models, we don't end up drawing these graphical model structures for you, we just show you the math, right? Okay, so then what we generally how we generally apply these models is that we take, so if we have some big, large Facebook network, we would take some small subgraph sampled from that larger network where that graph is fully labeled. So we see all the class labels that we're interested in. We estimate the parameters of the model from this fully labeled subgraph. And then generally what we do is we have some other part of the network where we want to apply that for prediction. And when we apply it for prediction, generally we know some of the labels of the nodes in this network. And so then it's similar to the kind of setting that Art was talking about, where we have partial observations in this network, and we roll out that graphical model and we do joint inference given the parameters that we had learned. And so when we roll out that graphical model and we have partially observed information about the class labels of the nodes, that also changes the structure of the graphical model. So here I'm just showing you the same rolled out version that I showed you before, but let's say for node 4 right here, we actually know its class label when we go to do inference, then the effect of that is that it breaks up the network because of the Markov property, right? So once, I guess I'm showing this in a little bit of a kludge, right? Because this known label can actually tell you something about these labels Y2 and Y3 over here, but it essentially, because of the Markov property, means the information here does not flow over here, and same for this information over there, right? And so when this particular node is known, you can almost think of it as two separate inference problems because the network breaks apart, right? And that's a very different situation than if we know this node over here. Oh, I went too fast. Because then you're only going to break off this little part of the network, and then you'll still have to do joint inference over here, right? So going back to the question that I think Matt asked Art about what happens when the labels that you have to seed things are not randomly distributed throughout the network, this shows why that can vastly change the kinds of results that you get, because now we have to do joint inference over a much larger part of the network. And if you happen to have a lot of labels that are randomly spread throughout this network, so if we have 80 or 90% of the nodes, we know the labels, that means effectively you're not doing inference over very large subgraphs, right? It breaks it up very nicely into a bunch of little small sections where you can do inference very accurately, right? But this might all sound very obvious to you at this point, but we didn't tend to draw these things for ourselves, right? So as Sophus knows, we painfully came to this understanding over many years of getting very distinctly different performance from different methods and different scenarios of label availability. Okay, so I have three main findings that I want to talk about in terms of how the work that I've done lately with my students have started to sort of highlight how the graph structure impacts the performance of these models. And some of you have seen some of this work already because I've talked, in the stat department here and other places in the Bay Area. And so I'm not going to go over the technical details, but just kind of highlight the conclusions that you might get from this work. And so the first set of work was an effort that we did on developing copula models for this kind of data, which I'll get to in a second. But the important conclusion of that work is that when we started doing work in relational learning to begin with, we looked at this IID assumption that conventional machine learning had made for many years, which is that the instances were independent and identically distributed. And we worked on removing the independence assumption, right? Because we explicitly wanted to exploit the relationship between users and their dependence to make better predictions. But what we forgot about was the other I for a long time. And so I guess we still, and I'm sure that Sophus will remember this, we still talked about how instances, users are users, right? We think of those as being identically distributed. That's what these templates try to do, to say, really, if you take a pair of users, people are essentially the same, right? If you know nothing else about them, the sort of likelihood that they share the same political views is, roughly the same across all people, right? Or that's one of the reasons that we can apply these models, because we want to say we take one large network, we don't just have one sample, we have a sample of n nodes in that network, right? And maybe our effective sample size, which has come up throughout the workshop, is not exactly n, but, it's something far away from one, right? We have enough data there in the network to be able to to estimate the parameters of the model. And so I guess I always thought that the way we define these models was essentially still assuming that our nodes were identically distributed. But actually, if you look at the way these graphical models work, because they depend on the structure of the network, the nodes are not marginally invariant, right? So if we know nothing about anybody in this network, when we make a prediction about the class label of A, we're going to marginalize over everything in their neighborhood, right? And although there's nothing there, we'll marginalize over the fact that we don't know anything in that neighborhood. And so that actually won't be the same prediction if we make do the same activity for this node E right here, right? Because although we still don't know anything about the people in his neighborhood, we know nothing about less people. If that makes sense, right? So because this node has only 3 neighbors here, it's different than this node over here, which has 4 neighbors, okay? And so we can't say that these are marginally invariant. And now we could have a discussion later on about how maybe they shouldn't be marginally invariant because they have different numbers of neighbors, right? So maybe that we do know something about them. But with our structures right now, we actually can't impose this implicit assumption that we had been making all the time, that they are marginally invariant, right? That was the assumption that we were making. And so more importantly, this Markovian relational representation that we're using doesn't even allow us to specify this constraint or ensure this constraint because of the way the models are rolled out over the network. And so what Rongjing did as part of her thesis was to think about whether there was an alternative approach and where we could impose this constraint in the model. And I won't go into the details because I don't have enough time, but essentially what we did is use a Copula-based representation where we're able to transform between a dependence structure across all the nodes, where we used a latent variable across the graph structure, which I'll show you in a second. And then we were able to transform between that joint dependence structure and marginals by using a Copula formulation. And so this is what the model looks like here. Let me back up. So you can think of what we did was actually construct an IID classifier where the effect of the attributes on the class label goes through a hidden variable here, z. And then what we do is we combine that with this joint representation right here, where now we model the dependence between the z's as this latent variable t, which then is rolled out over the network. And that's way too complicated to get into here, but the sort of key point here is that because we can separate the marginal representation from the joint representation, we're able to constrain the nodes to have identical marginals. Okay, so that's the key point that I wanted to make. Another sort of interesting point I wanted to bring up, so the way that we tie these together is that we have a latent variable, latent continuous variable, these t's that we modeled jointly, which actually then might be similar to what Art was talking about earlier, which we'll have to talk more afterwards about that. But then we have just a simple logistic regression on each node that includes, works the attributes in, and gives us a variable that then we'll use the sign of that to do our classification. And so, again, I'm very much glossing over the details, but the important and sort of interesting thing that resulted from that is that being able to impose this condition that we have marginal invariance means that across a wide set of, I thought these would all animate out for you, so this shows you an example of the kind of results we see on real data compared to a number of different kinds of relational models here, including some that are more feature-based, like this social dim model. And this RMN is the Markovian relational model. Here's the Copula model that does as good or significantly better than all of the current models across a wide range of conditions. And I should point out that here our x-axis is how many labels we have in the test data set, right? And so what this shows us, obviously it's great if we do better, we can get a paper published out of it. But what the key idea here I want to point out is that being able to actually put this assumption of marginal invariance into the model seems to be the thing that allows us to have this gain in performance. Right? And so this is something that we did not really think about as an effect of the graph structure, and to be able to constrain this while still dealing with this heterogeneous graph structure, we had to go through this complex machinery of Copula models, right? But if we think about more of these assumptions and how they interact with the graph structure, we maybe can get ourselves to better and better kinds of models. Okay. So now let me go on to finding number two. So finding number two is that the typical ways of using ensembles that have been widely used in machine learning to boost the performance that we have. I guess it's odd that I use the word boost there, right? So boosting and bagging kind of models that improve the performance that we get, the predictive accuracy. If we think about extending those to our relational domains, then we have to think about how to take structure into account, okay? So basically, if you think about a bias variance decomposition of the errors that we make in classification, now when we do these collective inference procedures, as we roll out this graphical model and do joint inference over the network, we now have an additional source of error that's due to the inference process that we use. And so let me just jump into that we have to be able to take that into account as we develop these kind of ensemble techniques. And so just to show you quickly what ensemble techniques look like if you're not familiar with them, in conventional data sets, what you would do is take a set of data that you have, somehow sample with replacement from it or do something else to get yourself many different versions of that data to learn models from. Then you'll apply all of those models to a test data set and do some kind of averaging or aggregation of your predictions in order to come up with final predictions. And so the sort of key components of these different methods are how to sample the data differently. So boosting will weight it differently after you make predictions about it. Bagging will sample with replacement, etc. And then how to aggregate the results at the end, whether you weight those results or you do simple averaging. So the question is how to do this for network domains. Well, the key issue that I know I've talked with a number of you about is how do we sample with replacement or in some other way from graphs when they're all interconnected, and we want to preserve the connectivity network structure. And the other issue is what can we do in here that takes into account that we're doing collective inference. So very quickly, Hoda in her dissertation worked on a relational resampling method so that we could get different versions of the same graph to use for training. And what we ended up doing is sampling subgraphs with replacement, which sort of goes back to this discussion we have about clusters as being the sort of informative units of the graph. We have a relatively ad hoc way of connecting those subgraphs back up to produce a large graph. So there's a lot more work that could be done in this area. But then we also developed a way to do interleaving of the collective inference processes to aggregate, instead of waiting to the end of the collective inference process, we aggregate the predictions during the collective inference process. And so what that would look like is that you have three graphs here where the edges between them, the nodes are all the same, but the edges between them might be different because of the different graphs. And what you're going to do is you're going to be making a prediction with one model in one graph, but you have three different graphs that you've sampled with replacement. And what you'll do is make your individual predictions. You might not have been able to catch that, but this node right here is mostly blue, and this is mostly blue. But in this graph, they think it's mostly yellow, right? And so what we'll do is we'll average those predictions before we go to the next round of inference. And this guy will become mostly blue because the other ones were blue, right? And so this interleaving of the aggregation while we're doing collective inference helps to prevent errors being propagated through the network because of some strange graph structure that you're seeing just because of variance in the data, okay? And so here are some results that sort of break down the gains that we get both from how we do resampling. So we could do relational resampling or I.I.D. resampling, and we can combine that with our collective ensemble, which is this interleaving process, or not. And this is the single model that we have right here. And so we get the kind of gains you'd expect to see based on the theory for bagging kind of results. And another thing I should note is that the gains get reduced as we have more and more labels in the graph, right? So these kind of bagging type approaches are going to work better or have more impact when there's fewer things we know in the graph. And so Hoda in her dissertation, and I think one of our papers, has a whole bunch of theory where she works this out for taking the bagging type theory to a relational setting to prove that compared to a single model in the domain, if we use a simple relational ensemble where we don't interleave things, we're going to at least keep the variance the same or reduce it. And then if we use a collective ensemble where we interleave them, we're going to further reduce the variance, right? So we can prove that we are going to reduce the variance. But the thing that I wanted to point out here is that in the proof of these methods, it's very interesting that we did not consider the graph structure. right? So our proof is really at the level of the predictive model, which is the Y's that we're trying to predict, right? And so we're kind of hand-wavy by saying that our graphs, we're not saying that the graphs are drawn from the same distribution, but we're saying the models of the Y's are drawn from the same distribution when we resample the network, right? So it's a very tricky way to try to prove things, and we just did it the best way we could. But what I wanted to point out was that I've thought a lot about if we model the graph distribution, can we say things about how our graphical models are going to perform given a particular kind of graph structure? And most of the time I argue that we need more work on how to model the graphs so that we can do a better job of saying these things. But actually this theory that we were working on says maybe perhaps there's a different way to approach it, which is to say, let's just punt on how to model the graphs if we can say that the processes which are rolled out on the graphs are the same, then the graphs are essentially equivalent for us, which might have some relationship to what Matt and Arun were talking about earlier in the week, right? So if we can take a step above and say that we can sort of not care at the base level about this exact graph that we have, but go one step up and say we're going to think about something at a higher level, that might help a little bit more with our theory. And because I'm running out of time, I'm going to skip the last finding. I am running out of time, right, Michael? Yeah. So I'm going to skip the last finding, and well, maybe I'll just put it up here and so that you can talk about it afterwards with me if you're interested. So the last set of work was thinking about model selection and how if we learn in a fully labeled network and we apply the models in a partially labeled network, then the performance of the models that we've learned is going to differ based on the graph structure that you have in your test data and the location of that label availability. Now, this is what I was showing at the beginning, because if somebody breaks, if we know this high degree node in the middle, we know it's labeled and it breaks everything apart, certain models might perform better than if you have only peripheral information that still keeps a big blob in your graphical model, right? And so I will not talk about the details of that, but if you're interested in that specific set of work, you can talk to me about it afterwards. So just in conclusion, we've had a lot of empirical success that shows that in many data sets, if we can incorporate these relational dependencies into our models, we can do a better job of prediction. But what we've not paid attention to is how this graph structure here affects the characteristics of our models. And so even though we're doing fairly well empirically, my feeling is that if we had a better understanding of sort of analytically or theoretically how this graph structure impacts the performance of these models, we'd really be able to push our methods to exploit that information even more so than what we're doing right now. And so having a better characterization of this graph structure, I think, is really needed to be pulled into the machine learning community and put together with a lot of the theoretical frameworks that we have already in machine learning. So I will stop there. Thank you.